All right, so the last time we met, we looked at this whole problem of radiative equilibrium, and we discovered that there were certain problems with it. Namely, compared to what we observe even in the tropics, it's too hot at and near the surface. It's too cold at and near the tropopause. The lapse rate of temperature is too large in the troposphere, which follows from the first 2 points. But, on the other hand, the stratosphere radiative equilibrium is not very far away from what we observe. So what's wrong with the radiative equilibrium solution? Well, there's a missing ingredient, one important missing ingredient, which is convection. In our atmosphere, particularly in the tropics, radiation is just one way that energy is transferred in the vertical. Another important way is convection. And so convection is just as important in radiation in transporting enthalpy in the vertical. But it also controls the distribution of water vapor in clouds, which are the two most important constituents in the atmosphere for radiative transfer. So everybody who's boiled water knows something about convection. This is just a little cartoon of what happens if you heat a pan of water with a flame. The water in the center of the pan gets warm, and warmer fluid is less dense, so it rises and sinks along the edges where it's cooled. That's the simplest idea of convection. Now, how do we figure out whether convection occurs in the real atmosphere, and if so, how much of it happens? And the first question we have to ask is, when is the fluid actually unstable to convection? When will it start to convect? So we're going to have to introduce three concepts here that are important. One is the idea of pressure, and something called hydrostatic equilibrium, which is the force balance of a fluid at rest in a gravitational field. The concept of buoyancy, and the concept of stability. So I'm going to talk about all three of those things